we discuss about ideal gas equation. Ideal gas equation means a mathematical equation derived from all the gas laws which explains the behavior of gases under given conditions. So, ideal gas equation is nothing but a mathematical equation derived from gas laws to explain the behavior of gases, behavior of an ideal gas under given conditions of temperature, pressure and volume. That is, now from Boyle's law, P is proportional to 1 by V or PV is constant. From Charles' law, V is proportional to T or V by T is constant, and from Avogadro's law, V is proportional to N or V by N is constant. So, now if you combine all the three, what we can get is that for a given N moles of gas at P, V and T conditions, we can write PV is proportional to NT or PV is equal to NT with a constant R, or this is in books in a standard way it is given as PV is equal to nRT. R is a proportionality constant. This PV is equal to nRT is the ideal gas equation. So, at a given pressure and temperature, V is proportional to N. At a given temperature for a fixed amount of gas, P is proportional to 1 by V, and at a given pressure for a fixed amount of gas, V is proportional to T. So, all the gas laws combined together that this equation is formed. Now, for two different gases at different conditions, you can write this as P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. This is another way of writing this ideal gas equation by avoiding the gas constant R. This R is what we call universal gas constant. Universal gas constant. Why is it called universal gas constant? Because that constant value is applicable for all ideal gases. It is independent of nature of the gas. For any ideal gas, whether that ideal gas we consider it is hydrogen, helium, neon, argon, krypton, xenon, carbon dioxide, sulfur dioxide. If you consider any gas as an ideal gas, then this value R is applicable. Then how do you define R? Obviously, this R is equal to PV by NT. For 1 mole of gas at 1 atmospheric pressure, if you take, then 1 atmospheric pressure and 273 Kelvin, that is at STP, this R is equal to 22.4 by 273, which is 0.0821 liter atmosphere per mole Kelvin, right. So, this is one form of, this is the actual gas equation, PV equal to nRT. This is an ideal gas equation. The other way of writing it is P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. This is without the gas constant R, this is with gas constant R. Now, how do we define gas constant R? Gas constant R is R which is universally applicable to all the gases. So, it is called universal gas constant. R is equal to PV by NT. For 1 mole of gas at STP, this R is nothing but 22.4 by 273, which is equal to 0.0821 liter atmosphere per mole per Kelvin, right. Then what is this value of R significance and how does it vary? How do we give it in different units, and what are the other different ways that we can arrange this ideal gas equation, that we discuss now. So, here this PV equal to nRT, this is one form of writing the ideal gas equation, or P1 V1 by N1 T1 is equal to P2 V2 by N2 T2. If N1 is equal to N2, then the same equation we write P1 V1 by T1 is equal to P2 V2 by T2, and if D is the density of gas, then you can have that as PV is equal to nRT. What you can write is N by V RT. This is equal to number of moles is weight by gram molecular weight. So, weight by gram molecular weight into 1 by V into RT. Weight by volume is nothing but density. So, it is dRT by M. So, from this also what we can write is that for a gas, for same gas at different temperatures, for same gas at different temperatures, P1 by P2 is equal to D1 T1 by D2 T2. This is another way of writing the ideal gas equation. Okay. So, like this, these are the various ways, different ways, depending on the information that is given, we can rearrange the equation and we can solve for any required quantity. So, this is how we determine, this gives us the relation even with the density also. So, for different gases under different conditions, or for given amount of different amounts of same gas under different conditions, this is how we write. And where when it comes to R, as I already told, now this R is equal to PV by NT. So, if N is equal to 1, then at STP R is equal to 0.0821, or before that I will put it as R is equal to 22.4 by 273, which is 0.0821 liter atmosphere per mole per Kelvin. This is equal to, in other units when we write, this is equal to 8.314 joule per mole, or this is equal to 2 calorie per mole per Kelvin. Now, here one very important point is that when we have to take which value of R, in which units that we should take, this is something very important. This is where normally the students will do a mistake while selecting the units and the value of R. So, if it is the questions related to this ideal gas equation, because in chemistry most of the times the volume unit will be given in liters and the pressure units will be given in atmosphere. So, while doing the problems related to ideal gas equation, let us stick to it to as 22.4 by 273 or 0.0821 liter atmosphere per mole Kelvin, because as I told, most of the times the volume will be given in terms of liters and pressure will be given in terms of atmosphere. Other than that, suppose if we want to measure the kinetic energy of a gas or the molecular velocities of gas, if any such information is required to calculate, then either we have to go in terms of joules or in terms of calories, and most preferably in SI units we take it as 8.314 joule per mole Kelvin. So, these two values you can take it for molecular velocities and kinetic energy calculations. For these calculations, use any of these two, and preferably this 8.314 is most preferred the one, but of course that depends on what units the parameter is given or asked, right. Suppose if the kinetic energy is necessary to be calculated in terms of calories, or if it is asked to calculate in calories, then take the R value in calories. If the kinetic energy is asked to find out in joule, then take this value, right. But then you cannot take this 0.0821, but for an ideal gas equation related problems, let us stick to by taking 22.4 by 273 or 0.081, because in this cases what happens is the volume given in most of the cases will be in the multiples of 22.4 and the temperature given will be in the multiples of 273 or in terms of 821. So, the calculation part also will become easy. So, next we will see some simple applications of this what you call ideal gas equation. And first of all, here also we define what is an ideal gas is. Okay. So, as this ideal gas equation, what we are giving it as PV equal to nRT. Now, what is first of all, what is ideal gas? For this, what simple way we can say is any gas that obeys all the gas laws or which behaves according to PV equal to nRT is an ideal gas. Any gas that obeys all the gas laws or which behave according to the equation PV equal to nRT, that means all the gas laws have been satisfied, then that gas is said to be an ideal gas. A gas normally will be an ideal gas. A gas behaves as ideal gas at high temperature and low pressure. At high temperature and low pressure, a gas normally behave as an ideal gas. Here, high temperature and low pressure, this temperature high, pressure low, these are not any constant or any demarcation. For different gases, high temperature means it will be different, and similarly low pressure also will be different. Then here the questions are that, so generally the question asked will be, for a 5% increase in volume, what will be the decrease pressure? This is one famous question, because normally what we say is P is inversely proportional to volume. We told that with increase in pressure volume decreases, or with increase in volume pressure decreases. When the question is something given like this, for a 5% increase in volume, immediately what you expect is that there will be a decrease in 5% of pressure, but decrease in pressure will not be 5%. Suppose if volume is increased by 5 times, then pressure will decrease by 5 times. Number of times will be same, but percentage is not same. Means for a 5% increase in pressure or 5% increase in volume, the decrease in pressure will not be 5%. It will be slightly different from 5%. How does it? If we look at it, suppose initial pressure is P, volume is V, 5% increase in volume, that is V plus 5V by 100. If this is P1, V1, V1, all this, and this is P2, then P1 V1 should be equal to P2 V2. So from that if you look at it, so your V2 is equal to V1 plus 5 V1 by 100 for a 5% increase in volume. This is now P1 V1 must be equal to P2 V2. So it is P2 into V1 plus 5 V1 by 100. So this relation if you take, so it is all nothing but P1 V1 is equal to P2 into V1 into, now this is 100 plus 5 V1, 105 by 100. So from this what you can get is P1 is equal to P2 into 105 by 100, or P2 is equal to 100 P1 by 105. So what I mean to say is that P2 is equal to 100 P1 by 105. So this if you look at this, this is 20 P1 by 21. So it is something less than, so it is less than 5%. This is what actually the meaning is. So this if you calculate, of course you can get it as right. This is where normally the students confuse. Okay. And similar this kind of some more problems we have, that where students normally going to confuse, the tricky questions 2 or 3 I will discuss now. Now another question normally that comes is, when a gas is heated in an open vessel, to what temperature should it be raised? To what temperature should it be raised so that 1/5 of the gas expels out? This is one simple question, but where sometimes the students confuse. When a gas is heated in an open vessel, to what temperature should it be heated so that 1/5 of the gas is expelled out? So immediately what struck to our mind is that first of all it is an open vessel, so pressure is constant. So at constant pressure immediately what we consider is that V is proportional to T, right. When V is proportional to T, or otherwise V1 by V2 is equal to T1 by T2. If you take this, then 1/5 of the gas is expelled. So initial temperature is T1. Now V2 is equal to, if you take V2 as V1 by 5, then what you will get is that initial temperature, so let me take initial T is 300 Kelvin suppose. So that means if this is V1, V2 is equal to V1 by 5, if you take, then this will become 5 1, then your 5 T2 will be equal to T1, or T2 will become, you will get it as, if V2 is taken as V1 by 5, which is actually wrong, because if you consider 5 T2 is equal to T1 or T2 is equal to T1 by 5, so that means you are getting less than T2. So, it is not heating. And another thing, this being an open vessel, on heating, volume is not changed, because it is the same vessel. So, volume is constant. Then what is changed? Then what here you have to take it as number of moles changes. So, it is N1 T1 is equal to N2 T2, or N number of moles, if you write in terms of weight by gram molecular weight, W1 T1 is equal to W2 T2. This is what you are supposed to take. Volume is constant. So, here what you should consider is P and V both constant. When P and V both constant, then you should take it like this. Then W1 is the initial, W1 into 300 is equal to W2, that is 1 by 5, W1 by 5 into T2. So, from this if you look at it, W1 when it gets cancelled, then T2 is equal to 1500 Kelvin. So, the gas must be heated to 1500 Kelvin from 300 Kelvin, so that it is 1/5 of the gas by amount. It is by amount what we have to take, not by volume. 1/5 of the gas is expelled, means it is by quantity, by amount, not by volume. This is how we have to take. Okay. Next. Another question is that suppose certain amount of dry ice, that is solid carbon dioxide. So, for example, 11 grams of pure dry ice means solid carbon dioxide, is heated in a volume, heated in a vessel of volume say 10 liters, then to a volume of 1 liter, 11 grams of dry ice is heated in a vessel of volume 10 liters to a temperature of 500 Kelvin from 100 Kelvin, so that all the carbon dioxide is converted into gas. Then find the pressure upon heating. 11 grams of dry ice is heated in a vessel of volume 10 liters from a temperature of 100 Kelvin to 500 Kelvin. Then find the pressure. First of all, before answering this question, the condition what we should say is that, well, first on heating from 100 Kelvin to 500 Kelvin, one point is sure that solid CO2 changes to gaseous CO2. So, then you can apply the equation PV equal to nRT. But the condition is that if it is an open vessel, then pressure is equal to atmospheric pressure, because in an open vessel the pressure exerted by gas is same as the atmospheric pressure. So, no need of doing any calculation, no need of doing any calculation, pressure will be equal to atmospheric pressure. Why I am telling this is, here when it is heated in a vessel, it should be mentioned here what kind of vessel it is, whether it is an open vessel or closed vessel, and also again in closed vessel a condition that whether it is previously evacuated completely or not evacuated, that also makes a difference. So, the case one is that if it is an open vessel, in case of an open vessel, pressure is equal to atmospheric pressure. So, no need of doing any calculation, to whatever temperature it is heated or to whatever temperature it is decreased, and whatever may be the volume of vessel we take, pressure is always equal to atmospheric pressure. And case 2 is, in a closed vessel which is previously evacuated. When the vessel is previously evacuated, then you apply PV equal to nRT. When you apply PV equal to nRT, 11 grams means it is, first of all what we have to find out is the pressure, and volume is 10 liters, and 11 grams is 1/4 of volume into 0.0821 into that temperature is 500 Kelvin, because that temperature is what we require. So, from this if you look at it, then this pressure is equal to 0.0821 into 500 by 10 into 4. So, this is, if you take it as, this is 50, 4 approximately I will take it as 0.041, 0.041 into 50. So, this is equal to 2.05 atmosphere. This is a normal straight calculation by taking PV equal to nRT. The next problem comes as case 3. If the vessel is not evacuated, if the vessel is not evacuated, then what comes is, then pressure will be equal to, final pressure is equal to 2.05 plus 1 atmosphere, that is 3.05 atmosphere. Why I am adding this 1 atmosphere? The reason being that the vessel is not evacuated first. So, already there is a gas inside the vessel, and that pressure is equal to atmospheric pressure, and then the gas is added. So, the total pressure in the vessel is equal to the atmospheric pressure at which already the air is present, and the increase in pressure due to addition of a gas, the total it will becomes 3.05. Okay. So, these are some tricky questions normally what we get. Okay.